So we will continue with this. So the next part we'll discuss about um, the scaling laws in electrostatic forces and also electromagnetic forces. Before that, I will have ask you a question. So what is the most common method that we will be actuating any component? Say for example, the fans or whatever that we are using in day-to-day life. What are the macroscopic components? How do we actuate it? What principle do we use? Electrostatic force or electromagnetic force? Which one do we use? Yes. So for the macroscopic ones, we use mostly electromagnetic principle. So do you think it would be the same for the microscopic as in MEMS devices as well? Let's find out. So first off, we'll start with scaling laws and miniaturization. Again, in this we'll see electrostatic forces. So electrostatic forces, we have like two parallelly placed electrically conductive plates. So these two plates are connected and voltage is supplied across it. So what are the dimensions of the plate? It has a width W and length L. And these two are separated by a distance D. So this is the distance between these two parallel plates. And a voltage is supplied across these two plates. Fine. So when this voltage is supplied across these two plates, there is an electrical potential field across this. So the corresponding potential energy in this is U equal to minus half CV squared. So we know that C is equal to minus C is equal to epsilon naught epsilon r WL by 2D. So what is the WL by 2D is the dimensions of the parallel plate capacitors. So what we get is the final we plug that C value in. So we get the equation as equal to minus epsilon naught epsilon r WL by 2D into V squared, since we have the two over here. So we get the new framed equation is minus epsilon naught epsilon r WL by 2D into V squared. Fine. So what we'll do is we'll find out what are the linear components, and then we'll equate them to we'll call them as L1. So we'll put them as linear component. So we know that epsilon naught and epsilon r are linear components with power 0, so they are not so we'll ignore them, and then W, L and D, these three are the dimensions, as in they will be given L power 1. So we also know that by Paschen's law, voltage can be approximated to we'll use a linear scale and we'll call voltage as L power 1. So what we get is V is directly proportional to L1 as per Paschen's law when we get a breakdown voltage. So what we'll do is we'll rephrase this, and so U will be proportional to epsilon naught and epsilon r are given as L power 0. So we'll give them as L naught and L power 0 and L power 0. And we get W, L and D as L power 1. And over here we have V square, right? So for that we plug this in and we get L power 1 the whole square. So the final answer we get is L power 3. So what happens here is a 10 times reduction of linear size of electrodes, with the electrode size are reduced by a factor of 10. What happens is the reduction in potential energy becomes 10,000 times. So here you can see that a 10 times reduction in linear size of electrodes, here you can see is 10 power 3 equal to 1000 times reduction in potential energy. So the potential energy reduces by a factor of 1000. Okay, this is where we use the electrostatic forces. Let's see the electromagnetic forces, how it fares out. So before going to electromagnetic forces, we'll use the equation and find out what is the electrostatic forces that are experienced on the parallel plate capacitors or the parallel plates. So here you can see that FD, we use partial differentiation equation and then partially differentiate it with respect to D, and thus we get as L power 2. So we get L square, and similarly for FW and FL with respect to the width and length, we get they are also proportionally equal to L squared. So we can conclude that FD, FW and FL, they are proportionally equal to L squared. So what we can finally conclude is that when there is a 10 times reduction in the electrode's linear dimensions, there will be 100 times reduction in the magnitude of electrostatic forces. So there will be a 100 times reduction in the electrostatic forces magnitude. So keep this in mind when we go to the electromagnetic forces.